Good day everyone, and welcome to our SUSE Linux Enterprise Server Training. My name is Jaco Foster, and I am a SUSE Certified Training Engineer for SAP Tech, and I will be your host for today. A huge welcome to everyone joining us for the training, locally and abroad. Now let's continue learning Linux the easy way. During the live streaming session, will I not be answering any questions on the chat window? However, one of my colleagues is on standby and monitoring this chat window and answering topic-related questions. It will be best if you could make note of your questions and rather ask them at the end of each session, or even better, send an email to suse@sabttech.com. Today we will be only using Server 1. So please ensure you have your Server 1 already started on your virtual machine. Let's have a look at our agenda for today. Today we will be covering the File System Hierarchy Standard, in short the FHS. Then we will look at Linux file types, and we will also be looking at the shell environment. So in order to learn Linux, we still need to learn and understand a whole lot of theory. And today is one of those days. We will be covering quite a bit of theory. Now let's have a look at the File Hierarchy Standard, in short the FHS. So the File Hierarchy Standard is part of the Linux standards base. The standards include the following specifications: which directories must be located on the first level and what the directories should contain. So the standard defines a two-layer hierarchy. Firstly, on our very top layer, which directories must be present. Now our top layer is known as root, and with root it is defined as with a front slash in Linux. Then also on our second layer, which directories must be under our /user directory and our /var directory. The FHS includes the following design factors: compartments, writability, and shareability. By compartments they mean separating out components out of the filing system to gain security and order. With writability, where can users and processes safely store files? Then shareability, who can access what, with and without the default permissions. The FHS is maintained by the Linux Foundation. Should you wish to visit the Linux Foundation, you can go to www.linuxfoundation.org. You can also visit the FHS standards at www.pathname.com/FHS. Now from my side, I have already opened up the web page for Pathname just to give you a quick overview. So here you can see I've got the Pathname website opened up, and you can go to a very top PDF file, version 2.3. Once you click on this, it will open up the PDF. On this PDF, you'll find more and quite a lot of handy information. You'll find a lot of standards which should be available on all Linux distributions. This is just one page as demonstration of what basic commands should be available on all Linux distributions and what they should do. Let's look at our first layer. Our first layer you will see starts with our root directory at the very top, the front slash. So all of these directories should be contained within a Linux system. So firstly we've got our bin directory where user binaries are stored. Then we've got our sbin where system binaries are stored. Then we've got our lib where libraries are stored. And only on 64-bit systems you will find the 64-bit libraries. Then we've got our etc where configuration files are stored. We've got our user, we've got programs and libraries and more. Remember we said user is part of our second layer, so we'll look into that shortly. Then we have our /opt where we've got optional and third-party application storage. Then we've got our /root. This is the root home directory if you remember in our first day, we stated that there was an X on it and we needed an access to our /root directory. So let's look at our /boot. This is where our bootloader files are stored, for example, grub2 in SLES. Then we've got our home directory where all our home users are stored with their home folders. Then we've got our /run where the runtime variable data is stored. Then we've got our mount directory where temporary mounted file systems for this session only should be stored. Then we've got our /var where variable files are being stored, and then we've got our SRV, site-specific data served for the system only. Then we've got temporary files in our /tmp. Then we've got our 3 directories created and populated every time on boot. This is our /dev, sys, and proc. Our device files are being stored on the /dev. We've got our /sys, where information about the devices and drivers are being stored. And then we've got our virtual filing system that works directly with the kernel and process information as /proc. So next, let's have a look at our second layer. Let's first look at our /user. Do you remember what the purpose for the /user is? That is where we store programs, libraries, and more. So within the /user, which is our second layer, we should only store the following. /bin is our most executables being stored for our programs. Then /sbin, that's where we've got system admin programs. Then we've got /lib, libraries and application directories. /share, where is our documentation and man pages are being stored. And then we've got our /local, where locally installed programs are. And then we've got our source code for kernel and programs. Let's look at our /var. So part of our second layer is our /var. And what comes under the /var? Variable files. So with variable files, they mean the lib, variable libraries like databases, log files for multi-user access under log, spool is our printer queues and emails, under run, information about running processes, and /log, our service log files. This is a view of a SUSE Linux file structure. You will see that the file structure is already very similar to what the FHS requires. We've got our root stated at the very top, and we've got all the listed directories as defined by the FHS. But we've got a few extras. In our boot, we've got grub2 running, which is our bootloader. In run, we define a media source for each user. Should you load a DVD drive on it, on let's say the root user, then it should automatically mount it to the media folder. Then a few others is our user folder is stated here with all the directories located under them. Our var is here also located. Then you will see on this screen there's a specific different color to the last 3 folders. These are the 3 folders which are defined by the kernel on boot time. They can change as the system progresses, and it's usually defined by the udev process. Next up, we look at our Linux file types. So in Linux, we have 7 different file types. Our first one will be our normal files, indicated with a minus sign. Then we've got our directories, indicated with a D, our links with an L, our sockets with an S, pipes and FIFOs with a P, block devices with a B, and character devices with a C. We will be discussing a few of them in detail, and others we'll just touch base on. Let's quickly have a look at the normal files. So with normal files and directories, we've got an example here at the very bottom. So this is an example from a command line. And you will see there's a lot to see in the command line, but we will be only focusing on this very first line. the two minus signs and the two Ds. So you will see that there's two minus signs which indicates our normal files. So what is a normal file? A normal file is sets of data addressed with one name. For example, this can contain ASCII files like settings, then executable files like programs and source codes, then graphical files like videos and photos. Then we can look at our directories. Here's our indication of what a directory would look like on command line. So what does directories do? It organizes files on disk, then it contains files and or even subfolders. Then the other purpose is to implement a security and a orderly file system. Now we look at our next file type called links. So we have two different links types. That's hard links and symbolic links, also known as soft links. Let's first see what each of them does. So a hard link is a secondary file name for files. Then we've got multiple file names referencing to a single inode. And then referenced file must reside on the same filing system. So our question is, what is an inode then? An inode is a filing structure created by the file system and managed by the file system to reference data or an inode directly to the sectors on a hard drive. So if this illustration is our inode and this inode refers to the sectors on our hard drive, we now have a file name a file name which references directly to this inode. Now we've got another file name with a hard link we have created referencing to exactly the same inode and in turn exactly the same data on the disk. You can create a hard link with this command, which is called ln, then a space, then your target file name, and then the link name you would like to use. Going forward, you will see I've created for every command we can run, there's a little arrow like this, and this arrow indicates commands we can utilize on our training environments. So let's look at our symbolic links. So we've got our symbolic links indicated with a L. What is a symbolic link? It references to other files on the system over a network or different volumes. A hard link must reside on the same filing system, meaning the same hard drive. Then the inode contained a reference to other file names, and its reference files can exist on the same filing system or on another filing system. This is what differentiates the symbolic link to the hard link. Then a symbolic link is sometimes called a soft link, and it can be referenced to a non-existent file, meaning a broken link. So if you look at this illustration, here we've got our inode with its unique identifier number, and this file is already linked to this inode. So all a symbolic link does, it creates a shortcut as we know it, from this file name to this specific file name, then in turn reference to the inode on the disk. If we want to view the inode numbers, we can use this command over here, and we can list the inode numbers as indicated with our illustration here at the bottom. Here is a more visual representation of links. So if we look at our two volumes that we have, hard drive volume 1 and hard drive volume 2, and our data resides on our sectors at the bottom, and then we have our filing system which manages our inodes at the top. So this green indicates our inode. So inode is linked to the physical data on the drive, and we have a file name linked to the inode, which is our data. So when we create a symbolic link or a soft link, we can create its own inode on another system and reference this directly to the path of this specific file on another system, whether over the network or just on another volume. It can be created, very similar to a shortcut. Then when we look at a hard link, if we look at a hard link, it must be created on the same volume, on the same filing system. Now this hard link doesn't reference directly to the file, it references directly to the inode, and the inode again to the data in return. So this file and this file will have exactly the same inode number which they share. Let's do a quick practical exercise on links. I'm going to go back to slides so we can see the instructions. I've got my server 1 already started up. So here I would recommend you to just rearrange your windows so you can follow me on my server, and you can follow your own instructions on the server as well. So first up, let's quickly right click on our desktop over here and we click Open Terminal. I'm just going to increase the font or the size of my terminal so you can view it better. We go to View, Zoom in, and you should be able to see a lot better now. Alright, so where are we currently on our directory structure? In Linux, in SUSE Linux, your home directory for your user on your current server is indicated by the tilde sign, which is our home directory. So to see in which directory we are, we press print the working directory command, pwd, print working directory. And it will tell us where are we currently at. And that's in our home folder /tux. So let's list what's within our tux folder. So let's go ls. So the ls command lists all the documents and folders. We can also use ls -lt to get more detail. So let's create a new file. To create a new file, we are going to use the echo command. Normally we use the touch command, but for this exercise we're going to use the echo command. So now we're going to type in echo. And we're going to type in what do we want to add to this file. So we go echo underscore for that matter, and we'll add that information to a file called test.txt. I need to put a dot in there, txt. So now let's list our files again, -lt. So now you'll see at the very top we've got a test.txt. Let's see what's inside our test.txt. For that we use the command cat. They'll put a word in test.txt. And there we can see we've got the word hello underscore. So let's see what's the command or what's the inode of my file. For that we're going to use the command listed at the bottom, which is called ls -li. Okay, so it's ls -li. Now we can see what's the inode number for my file test. On my system it's 33595. It should be different on your system. Let's see what's the contents like on this file. We go cat test.txt. And it's still the same contents. Okay. So next up, let's create our symbolic link. So we're going to use this command at the top over here. So a symbolic link will be the ln -s command, and we will create our target will be test Because we are in the same folder, we don't need to specify the path. We can just type the file name directly. And then our new name. So we'll call that softlink underscore test.txt. So let's list our files with the ls minus li. Now we can see that we've got our original file, and now we have a soft link which points to the test file. Let's view the contents of our soft link. For that we will use cat and then soft link. You can use the tab to autocomplete your sentence. Use tab. We'll discuss that a little later in more detail, but this helps to type quicker. So if we hit enter, we will see we have the same contents, which is called hello underscore. So after this, let's add some more data to this file. So the easiest will be, let's use echo again. We go echo and we say world in there. So they should be world, there we go, world, and we add that to our soft link underscore test.txt and hit enter. Now let's go view the contents of our soft link again. We go cat softlink.txt, and I've just overwritten my data. I made a little mistake, but that's not a problem. If we have overwritten the data, that's fine. Let's see if it's added that data to our test file. So let's add the let's view the test file, and our test file contains exactly the same data at this stage. So now we know that we've created a symbolic link to a specific file containing the same data. So next we're going to create a hard link to the file test. And what's interesting and what we should note is the current inode name. So let's do this. Our test file will go ln, and then our target will be test. And this time we will call this hard link underscore test.txt. And we'll hit enter. Let's go list our files in here first. We go ls minus li to get our inode numbers as well. And let's see what happened. So we've got our original file called test. And now we've got our hard link called underscore test.txt. And take note of the inode numbers. They are the same inode numbers. So they refer to the same data on the drive. Now something else has changed. Who can tell me? Have a look. See if you can notice that. If you look at our very first test file over here at the top, you will see there was a number 1 over there. But once we created the hard link, it automatically created a number 2 to define that there's more than one link to this specific inode. Alright, so let's do a test on this quickly. We are going to add some more data to our hard link this time. And let's do that by doing echo again. Echo. And then we're going to do an underscore world or hello, sorry. Hello this time. So the text should read world underscore hello if we are right. And we're not going to do overwriting the file. We're going to append the file. So with that you need to put 2 of these appendix files or signs in. characters is the right word, characters. And then we're going to use the hard link this time. Hard link underscore test dot txt. So let's hit enter. I'm just going to confirm my spelling is correct. That is perfect. And let's go view the contents now of the hard link. Let's go cat hardlink.txt, and we've got now world hello in there. And let's go view the contents of our original file, cat test.txt, and we have the same information in there. Let's go and view our soft link in this case. Cat, our soft link, and we have exactly the same information in there. So what we can take from this is the moment we create a normal soft link, it creates a new inode number, and that inode is now linked to the data within our original file, in this case called test. When we create a hard link can only reside on the same filing system, and it shares the same inode number, and the inode refers to the data located on the sectors of the hard drive. Now for fun, let's break our system a little bit. I'm going to go and I'm going to remove our test.txt, and let's see what happens. Let's go rm for remove test.txt and hit enter. So if I'm going to list what files in here, the test.txt should be gone. So ls minus li, because I want to see the inode numbers. And something happened. Immediately we've got a red text over here stating that this file is missing. We can no longer access this file because the soft link is now invalid. But we still have our hard link, and a hard link still refers to the same inode. So I've removed the original file now. So let's see if the data is still intact after removing the original file. We go cat hardlink.test and see, and we still have data in there. Let's see if we can cat the soft link. And the soft link is broken. There's no such file or directory. So how do we fix this? Easiest is, let's create another hard link. So we go ln, and we're going to create our target. This time is going to be the hard link. I've tabbed it out so it auto-completed. And we're going to create our original file which was lost or removed. Text or test, let me just get a test.txt. Now I've done that and I hit enter. And let's view the contents of this file. We go ls minus li to view the contents. And it has restored my link, as you can see. It's restored the inode number with the test.txt. And let's go list our contents of test now. Cat test.txt. Oh, I just need to get my fingers right. There we go. And we have our content back. So this brings us to the end of this exercise. Let's continue with the next file types. Now we move on to the next file type. Let's look at sockets and pipes. So we've got a socket, and a socket is indicated by the S. And what's the purpose of a socket? A socket is a logical endpoint for communication between processes. It's used for two-way communication, and it's indicated by the S when we look at our illustration over here. Then we have pipes. Pipes is also called FIFOs, first in, first out sometimes, and it's indicated by the P. So it's a logical endpoint for communication on a file system for output from a process. It's used for one-way communication only, and multiple processes can read from a pipe. So a pipe is indicated with a P. In our /proc directory, we will find many pipes and sockets. So let's carry on to the next file type, and this is called device files. So what does device files do? Device files represents hardware. So this is the link between hardware devices and the kernel drivers. Kernel drivers read from and write to the device file. The kernel gets the data to the hardware in a correct format. So our kernel acts as the interpreter to interpret our instructions for the hardware devices to understand what we expect from them. Then when we refer to network cards, they have their own method of communication. So the two types of device files we get, it's called block devices and character devices. Block devices carries the B indication and a character device the C indication. Just a quick important note, device files are automatically created by a system tool called UDEF. There are tools for circumstances when manual creation of device files are necessary. This means that we can create driver files to communicate with drivers manually, and we don't always need to rely on a kernel. It's possible to write our own drivers when it comes to Linux. Let's have a look at our device file called block devices, indicated by the B. So what's a block device? A block device file are primarily used for storage. So to give you an idea, the first initialized drive will be referred to in /dev as SDA, maybe solid disk A or SATA disk A. Then our second physical drive will be called solid disk B. So once we want to create the partitions, our partitions have their own naming conventions, and the partition numbers are appended to the device name. So our first primary partition on SDA will be called SDA1, and once we create a second partition or even an extended partition on the first drive, it will be called SDA2. So if we have a third hard drive installed on the system, then this will be indicated as SDC, and our first partition will be called partition 1 of SDC, SDC1. Then our first logical partition will always be created at number 5 of the drive. Doesn't matter which drive you have. We will go into more detail on logical partitions a little later in our course. So our second logical partition will then be indicated on the first drive of SDA6, the second logical partition. To give you an idea, it's indicated with a B in our snippet over there. Our next device file is called character devices. It's indicated by a C. So our character devices provide unbuffered access directly to the hardware, sometimes referred to as raw devices. So many different options for character devices make use of the application wide and varied. So we've got a lot of purposes for the character devices. Some examples of character devices are our keyboard and mouse. This is indicated with the C in front. Our next topic is the shell environment. What is the shell environment? The shell environment is the most basic user interface to the SUSE Linux Enterprise Server. It's also referred to as the command line interface, called the CLI. There are multiple shells available in SLES, and they are listed in our /etc shells file. Now the default shell for SLES is the bash. Bash stands for the born again shell. Now there are other shells you can also use. For example, C shell, corn shell, enhanced C shell, and the Z shell. There are many others. When you look on our right hand side, here is a list of all the available shells within SLES. We'll quickly do this as a practical exercise so we can see exactly where to find the shells. So let's quickly open up our server. I just need to find mine quickly. There's my server. Great. So let's clear the screen. To clear the screen, we go clear and we hit enter so we can work with a clean environment. So now we would like to know what's the current shell that's available for my current user. On the next slide, I'll explain more detail on how this works, but for now, let's quickly see what's my current shell. So we're going to do an env to find my environmental settings for this user. And oh my word, there is so much data in here, we have no idea where the shell is located. We know it's somewhere in here. There should be an easier way to find our shell. Let's try that quickly. Now we know that the name is shell. So let's do the env again. Now with the env, we are going to use a pipe. That's the little character that's on top of your enter key. It's usually with your backslash key. With this key, when you just do shift and you press that key, it will give you a pipe. Now for a pipe, we'll explain that also a little later how you actually use it, but you can take the output of a command and redefine it as an input for a next command. So we're going to use a command called grep, and we're going to define a grep takes a certain text, like grabbing text from an input. And now we're going to search for the word shell. So we do env space pipe space grep, then space shell. And let's see if we can redefine our output. Oh, wonderful. So if we look at our output now, where we have added our command, we now can see that for tux user, the environmentables is set that it must use the /bin/bash shell. So let's list all the available shells. Let's clear our screen first with the word clear and hit enter. And now we're going to list all the shells. We go ls/etc/shells. So this should list all the available shells for the system. Sorry, not the ls, that's my mistake. We need to do a cat of the file. And there's our cat. Now we can see all the available shells that is registered on our system and where they are located at. Go back to our screen. Okay, so we have run the command env pipe grep and shell, and our output was exactly this, env pipe grep shell, and we could redefine our output to find the shell which the tux user is using currently. The shell environment is made up of components. So some of these components can be customized for the user preference. For example, we've got variables, functions, and aliases. So variables are the most commonly customized part of the shell environment. Then we've got functions to define the core functionality of our shell. And then aliases. It allows shortcuts to long and complex commands. for using a shorter input. We'll look at that shortly. A shell can be invoked in two different ways. We get a login shell and our non-login shell. So our login shells. The user's preferred environment variables, function aliases are set. So a login shell will be asked for your username and password. Here's an example of a login shell at the bottom. It will ask you for your username and password. Then the login shell can be requested with the -- login option when bash is called. A non-login shell over here over here is the shell inherits an existing environment from a previously started shell. So a non-login shell will not ask for username and password, for example, our known terminal session. This has been the shell that we've been using for all our exercises so far. Let's look at our shell in variables and settings. Now, we're not going to go into too much detail, but what you do need to take note is that you can change the variables for all users. And the all users variables are usually loaded first when calling a shell. You'll see the etc/profile is listed first. Then, when you call your user-specific profile settings and variables, those are located in your home directory .profile.bashrc and .alias. So those are called later when opening up or calling a shell. So you will see they are loaded close to last when calling a shell. Whether it's in a non-login shell or a login shell, they are a little bit more later when it's called. So it will have more recent data if you want to understand it in that sense. Taking a deeper look into aliases. So we already know that the shell alias is there to create a shorter name. So some of the alias commands that we can use is alias with an unique alias name equals and then the command that we want to run. Now this command must be in inverted commas to be able to let this work. So to remove an alias, we use the unalias command and then the alias that we have created. And then to list all defined aliases, we will use the alias command. Our alias definition file is located in the .alias. So let's quickly have a look at our practical. Let's bring up our server and see if we can run some of these commands. So this was our last command. I'm just going to clear my screen so we can start fresh. So let's run our alias command first and see what aliases is defined on our system. So let us get there, type in alias. And here we can see which aliases is defined for our system. So let's create a new alias. And one of the commands that we ran earlier was our ls minus li. So let's quickly do a command for that. So we type the word alias, and then give it a name. Let's call that our li command, and we'll equals that to a ls minus li. And we put that into we close inverted commas, and we hit enter. Let's first go see if our alias is now listed. And we should get a li, which will now define as a ls minus li command. So let's try that. Li should now list our inodes with a shorter description instead of typing the long name. We can also remove this by using the unalias command. So we use the unalias and then we do a li that we say. and that should remove it. And if we put alias in there again, we should see that our li has now disappeared. Let's continue to the history command. So with the history command, everything that you type is being logged into a file. So when a command is entered into the shell, it is stored into the history file of the user who executed it. In this case, our home directory .bash_history. To view the history file, we just type in the word history. We can also search the history with the Ctrl+R, and we can tab through it and hit enter once we get the command. In my experience, I found the search to be a little buggy, so we'll see how we go in this course. If you want to re-execute a numbered command from history, you can just type the exclamation with the number and you'll be able to rerun that command. For example, if we wanted to see the VI, we want to run a command vi/etc host, all we had to do was put the exclamation and the number 3, hit enter, and it would display the history or would run a command for us. Let's quickly open up our server to be able to run these commands. Let's clear out our screen first. So the first command we're going to run is the word history. This will give us a list of all the recent searches that we have done. So I'm going to try to run one of these commands and we're going to search for it and see if we can rerun the same command. I want to run a cat. So let's go Ctrl+R and we go search for cat. So there we go. There's our cat. And now it automatically brought up the full command. Once we hit enter, it will show us the complete command or rerun the complete command. Let's do something else. Let's see if we can rerun the ls/etc/shells. My number in my history is number 95. Yours should be different. So to do so, we will do exclamation and the number 95 and hit enter. And that should rerun that command for us. There we go. So it reran that command for us. Something more in detail. Let's go and let's see what we've got here. Let's cat the test. So we run number 83 on my site. Cat test. You can choose any of your commands you would like to rerun. So I'm going to do exclamation and number 83, and that should run my cat test command for me. Now let's quickly have a look at our tab autocomplete. Now we've been using this command a bit, and the command is utilized when a command, or the tab is being utilized when a command becomes difficult to type out, and a list of possibilities can be displayed by also using the tab command. So here in an example, we have typed in the word his. So with the word his, when you hit tab, it auto-completed to history. So for example, if we now type in a word hi and we hit tab once, we'll see it does not autocomplete. So then we had to hit tab another time. So the second time we hit tab, it will give us a list of all the commands that can be run with the hi. So that tells us we just need to put in an S afterwards because we want to run history, and then tab it out again and it will complete the command for us, and then hit enter. So let's look at data channels and shell redirection. Now this becomes a little bit more difficult, and this is where we need to concentrate on what we do. So we're not going to go into too much detail on everything, and we have touched some of the commands already. So we will not be doing some of the commands again. So to give you an idea, we can redirect data into a file. Now we have used this command before, where we have redirected data into a file. But before we can do that, we need to understand how a process works. So when we look at the in of a command, it starts with a process ID of 0. So then a process operates, and then it either has a 1 or a 2 output on a process. 1 means the command or the process was successfully entered, and it will provide us an output. If there is an error in our command, it will automatically revert to the ID of 2, and then the command will not process, or if there is an error associated with the command, it will give us the error output. Now, let's see how we can utilize this process or commands to do some changes or make some changes to our system or run commands. So an example of a redirect is if we're going to list everything within our /etc directory, then we want to output this to our temp folder and under the etc_files.txt. Now we've used this earlier with the echo command. So we've typed in echo and we want to output that to a test.txt. Now we can also amend a file, also append a file. To do so, we will use the double redirection command. And that will only make changes to the file and not overwrite the contents of that file. We've done that with the echo command also earlier, where we've added echo and then a double redirection and our echo and then obviously the text we wanted in there and a double redirection and then the name to where the file or to the file name. So you can also redirect the error into a file by using the to in a redirect. You can amend a file, so you can add continuous error to the same file. Then you can redirect into, let's say, text into a mail service. Then we have used the pipe functionality already, where we've redirected the output of a first process into the input of a second process. So how does this work is we go ls/etc. So this will list everything within the etc directory. So that will be our first command. It will be the input and it will successfully execute to the out. So the moment we use a redirect, the pipe basically goes over here. And that becomes the input for the next command. In this case, we use the T. And the T in a file and it redirects it to a terminal. We can also run multiple commands by using a semicolon. So to chain multiple commands together on a single command line, you can run, for example, echo hello and then semicolon echo how are you, and it will write this for us it will execute both commands with a single enter basically. Then we can also do the double ampersand. This will execute a second command only if the first command returns no error. So a double ampersand we can create to run a process in the background. So we'll get through our exercises and we will later on work in more detail with this as the course progresses. Now let's quickly look at our help resources. Now there's so many commands in Linux that we can refer to, and there's so many ways of reaching the same output by just a different method. So there's a few ways that you can find or you can run help or find help within Linux. The first one will be if you have your command and you say command, for example, history space -h should give you a short list of the help. The same goes for the command minus help will give you the same output. But then is full explanatory manual pages which you can run. So you can run man, and if you know the section number, you can add it there, or you just go man and the command. For example, man and history will give you an output. So to list for keywords, you can do the man minus k keyword and it will find the keywords. Then display descriptions. You use the what is command with the command that you are querying. Then you can do also info, and you can quickly query the info pages with the info and then the command. Now, all of our documentation are listed under the user share doc packages for the software packages, and then release notes available under user share doc and release notes. So let's quickly try some of these help commands with our server. Just going to open up my server quickly and let's clear our screen. So let's try some of these commands. Let's quickly do a cat -h. I didn't find that to be very effective, but I do know that a minus help is more effective. So here we can see a quick overview on what cat can do and some of the options that we can utilize with cat. Then we can go to the man pages for cat. Should you not make a selection, it will automatically direct to the one with a star and will open up that man page within a few seconds. Here you've got more detail which you can view on the cat options and functionalities. You can do this for just about every command within Linux. So let's quit this and let's try the what is command. It will give us a quick description of what this is. So let's go what is cat, and it will give us a quick description on to print our files. Right, and then we can also do info. Let's go info on cat. It will give us a quick understanding on what cat can do. Very similar to our man pages. You can play with this on your own time. Hit Q to quit. Now that brings us to the end of today's session. Thank you for your valuable time and joining me for the training. We now have a few moments to answer some technical questions. For any longer technical questions, please send us an email to suse@sabttech.com and we'll answer them as soon as possible. The recording for today's session will be uploaded to YouTube, not to Twitch as previously stated. So if you go to YouTube, let me find it here. There we go. You go to YouTube and you go search for SABT Tech and it will bring you to this page, and you can subscribe to our page and also enable notifications to get notified when the video gets uploaded. Great, now that's all from me for today. I'll see you tomorrow, same time, same place. My name is Jaco Foster from SABT Tech.